Okay, so let's start a technical discussion on your course titled Deep Learning, right? So this is your first lecture, so of course, major proportion of today's discussion will be focused on introductory concepts, right? So what all we'll see today, I'll just give you a brief overview. So definitely we'll start with some discussion on course and course policies, okay? Then I'll briefly introduce you to what deep learning is, and after some discussion, only then we'll be in a position to discuss the course contents, okay? And then I'll introduce you to the popular deep learning software that you can use, right? Some libraries, Python, and what you need to install. Then we'll see deep learning data sets, right? What are the common data sets? What are the benchmark data sets on which you can test your algorithms? And then for a given problem, how do you choose a deep network? We'll discuss that. Then we'll see some resources like what are the good journal papers, what are the good journals and conferences from which you can borrow ideas if you want to do some research. And then I'll give you some implementation guidelines that how you can actually install deep learning software and come up with solutions which are based on deep learning. Okay, so as you must be knowing that machine learning is the official prereq for this course, right? But even if you have taken a similar course like pattern recognition, then it's okay. That would do the job. But other than that, we also expect that you have some basic knowledge of probability, statistics, and to some extent linear algebra, right? So these are a few concepts that would be used during different topics of this course. So you must have seen the timetable. We have one session per week, that is Wednesday 5:30 to 8:30, okay? So that you already know. And then for the course resources, you have LMS, right, which is already there. But I asked you through your CR to join Piazza as well. And the reason is that LMS is in the process of evolution, right? It is being evolved on daily basis. And presently, I don't have any facility to make announcements through LMS, right? So on Piazza, it's fairly simple for me that I can simply post an announcement and it reaches every one of you, right? So that's why we opted for Piazza. So you can choose any of these, right? Everything that is available on Piazza that will also be made available on LMS, right? But since Piazza also has the flexibility of making announcements, so I expect that you check it at least once in 24 hours, right? So that you do not miss anything. Okay, so I think almost all of you have already joined, but in case if any of the students could not join, so you can simply join your course, and the access code is DSC707, which is the same as your course code for deep learning. Okay, so from the perspective of books, as you all know that it is a fairly new domain, new buzzword, right? So you won't find a lot of books on deep learning, right? But still there are some good books which you can find in the market. For example, the first one that you see, 2018, it's a good book. You can easily find it in the market. I'm not sure if the PDF is available, right? There are other books as well which I have listed, but I would recommend you that if you need to get the latest knowledge, then you have to see the latest research papers, right? Because even 2018, it seems relatively recent, but in the context of deep learning, 2 years is something very old, right? Because in deep learning, things are like changing every few days or weeks. So that's why 2 years is a big gap. So I would recommend you that do go through latest research papers. If you are doing a thesis, then you should consult the recent papers which are most relevant to your problem. Okay, so since we are in an online mode, right? So definitely we'll discuss later on with your CR and all of you that how do we implement assessments, right? But one thing is for sure that we'll have assignments, and almost all of the assignments would be a mix of implementation and research, right? So implementation does not mean that you have to write code from the scratch. You will be free to borrow the code from anywhere, right? I don't want you to write programs from the scratch. You can borrow a code from anywhere. What I want is that you should be able to reuse that code for your own problem. and then come up with a meaningful analysis, right? For example, if I give you a problem to solve using neural network, you are free to borrow a code which is solving a problem with neural networks, apply it to the data which I have given you, and then do some meaningful analysis, right? So this would be almost all of your assignments would be like this, in which you will have to prepare a technical report, which is very similar to how you write a research paper, right? And of course, we are in a graduate class, so I do expect that you will be submitting assignments on time because you submit them through system, and there's a specific date and time after which the system is locked. So there's not much we can do about it. Okay. So as far as the final and the midterm assessment are concerned, for the time being, we ignore it. We'll discuss it later, right? Maybe things change, so I'm not sure. It will be online, it will be on campus, right? I have the same information as you. So as the things evolve, we'll discuss it at a later stage. Okay, so for all the assignments and any exam or assessment, right, my rule would be that I won't expect you to memorize anything, right? Because you see, it doesn't make sense that we memorize things that we can always look up for. For example, I would never ask you what is the Python function for this, how do you do this, what is the formula for this. Okay, so all of your assignments would be based on things in which you would not need to memorize anything. Okay, you just have all the data available. You can look up, you can borrow code, you can borrow derivations, formulas. That is perfectly legal in every assignment that I will give you. Okay, this you already know, but for completeness, I'll just repeat it. You know that in MS and PhD programs, the passing marks are not 50%, they are 60%, right? And we have a standard distribution, which is like 10% for quizzes. Then for midterm for assignments 20%, midterm is 30, and final is 40, right? So if it stays like this, well and good. If it changes, I'll update you as soon as I have some new information. Okay, so slightly let's dive into some slight technical details. So you know that this course is being offered to as a core course to students of data science, right? And then we also have some students from MS Computer Science and maybe a couple of PhD scholars as well, right? So it's very important that you must know where this course fits in the overall objectives of your degree program, right? So I'll be talking in the context of data science side. So you know that the objective of data science is basically that you have to extract meaningful information and insights from data, right? Which can be structured or unstructured. And of course, data science is a specialization in computer science. So deep learning is a tool, but not the only tool, but it is a very major tool that will help you achieve this objective of extracting insights from data, right? So you can use deep learning as a tool, which will eventually help you to achieve the objectives of your degree program, that is Masters in Data Science. So if we discuss it a little further, so let me just, sorry. Yeah. Okay. So you see, if we see from the perspective of where data science stands in terms of computer science, maths, and domain knowledge, so you see it's a cross between CS, mathematics, and domain knowledge, right? And you must be wondering that, okay, what is actually this part, okay, and what is this part, and what is this part? So I think you can guess that if this is data science, which is actually using something from computer science, mathematics, statistics, as well as domain knowledge. So if I'm talking about this part, right, this one, then this is computer science and mathematics and statistics, right? So maybe we can call it machine learning, right? It makes sense. And then if we are talking about mathematics and domain knowledge, then this is something that you would commonly call maybe data analytics, right? And if we talk about this part, computer science applied to some domain knowledge, then this is like traditional software development, right? In which you apply your knowledge of computer science to solve a given problem, right? So here you can see the complete, you can say, a taxonomy that where every component fits in. Okay, so for the perspective of this course, right, you must be knowing that we have a broader umbrella of artificial intelligence, within which we have machine learning and then deep learning. And as I told you, you can solve many data science problems using deep learning, but not all of them. There are other ways to solve data science problems, right? So for this particular course, we'll be focusing on this part, that is deep learning. But it is always important to understand the difference between AI, ML, and DL. These are highly related terms, but as you have seen in the previous slide, that every component is a subset of the previous component, right? So the big umbrella is the AI, where we aim to develop techniques which allow machines to mimic the human behavior, right? This is the general objective of AI. Within AI, we have a certain category of methods where machine can learn based on examples, machine can learn based on experience, and that is called machine learning. And within machine learning, we have this deep learning, which is actually the focus of this particular course, where we will be dealing with the study of neural networks, which will have a large number of layers between input and output, right? I'm using this terminology neural network because I assume that you must have studied it in machine learning. But even if you don't remember concepts related to neural network, don't worry about it. I'll be covering them in detail in the next week. Okay, so if we try and track back from a historical perspective that when AI started, right, it's very hard. Different people would have different opinions, but one very initial sign which relates somehow to AI is basically by this French philosopher in the 17th century, when he claimed that one day machines would be able to think and make decisions, right? So today it does not seem like a big claim, right? It does not surprise us. But if you think that this claim was made in like 17th century, so at that time, no computer, no nothing, just electronic circuit. So you can see that we feel like appreciating this guy, that at that point in time, he was able to foresee that there would be a time centuries later, machines would be actually making decisions. And this is to some extent true today. Okay, so if we try and see what are the major milestones that AI has achieved, okay, there are many, but of course we'll try and list few of those. So starting with early 1960s, right? So you can say, Lisa, this was the first chatbot program. Okay, if I don't know, maybe you're not that old, but if you did your bachelor's like 10, 15 years ago, so in the AI lab, Elisa was the software that you used to play with, right? It's like a chatbot. You can talk. You can, in natural language, you can talk to this chatbot and it will respond to you, right? So it was in the early 1960s that this was developed, which is like 50 years, rather 60 years back, right? And then you see self-driving cars, they have been there for a long time, but the first actual, you can say, successful experiment was in 95, where a completely autonomous car was able to drive from Munich to Copenhagen, right? But today you see they are very common, but the first successful drive was back in 1995. And then in 97, there was IBM's computer, which was able to beat a human in a chess, right? This was again a very major breakthrough, because prior to that, we could not expect computers to beat human on such problems. And then recently, 2010 Siri, which basically is a major breakthrough in natural language processing, right? It was later acquired by Apple, and then you see it has been now integrated into the iPhone. Then in 2015, like 5 years back, there's this famous statement that machines can see better than humans. Now, what does that mean? There's a visual recognition challenge in which humans and computers were shown different pictures, right? And the task was that they had to tell what they see in a picture, okay? And there were like, I think more than a little around 1,000 categories. So in that particular challenge, computer was able to beat human, right? Means there were few pictures in which human did not know what is it, and the computer was able to tell. That was back in 2015. And then 1 year later, there's a very, you can say, famous game Go, and again, a machine learning based system actually beat human experts in this particular game. And as I said previously, that maybe in the 90s, self-driving cars were only in the experimentation phase, but but today you can see them running on the road by like Google or Tesla and so on. So when we have these achievements, then we are tempted to think that, okay, what will happen maybe 5 years or 10 years down the road? Okay, what you can predict, what new applications we can think of that they would be coming in the subsequent years, right? So of course, there are many you can think of. I have listed a few. So for example, maybe after 10 years, there's no Hollywood, there's no Bollywood. You can have computer generated videos, right? Computer generated movies, whereby by just analyzing your preferences and a customized movie or a song or serial is generated for you, right? That is very much possible. Similarly, you can have virtual assistants. You don't need to tell them anything. They can observe your pattern, your behaviors, and they can predict what you want, and they can place orders for you, and they can do other tasks without you telling them, right? And robots, they are already there. And maybe this is a bit debatable. Maybe someday, when we say fortune teller, it's a bit of exaggeration. But you see, when we are making prediction, we are actually telling the future. Not in the sense of a fortune teller, but still, when you predict something, that it's like predicting future, right? So maybe with further developments in AI, this matures as well, right? You must have seen studies that by reading Facebook posts, people or systems are able to predict suicidal tendencies and so on. So it is like making a prediction in the future. Not exactly the same thing, but very close to it, right? So once you develop these things, of course, you would be needing technology, right? And maybe for such applications, the existing technology would not be sufficient, right? So from the perspective of technology, although that is not the objective of this course, but still you must know that maybe after 10 years or 15 years, we are not talking about CPU or GPU. Maybe we are talking about quantum computing, right? Because with such heavy applications, maybe the current hardware resources would not be sufficient enough to be able to run these or run similar systems. Okay, so basically, as I told you that the interest in artificial intelligence, it actually dates back to the early 50s, and then the terminology of machine learning, it came to scene around in the 80s, and then it was in the 2010 that people started talking about deep learning, right? And if we elaborate this timeline a little further, right? So there are many milestones, but of course, from the source from where I took this, so I like this one. So basically, in the 40s, you had something which is called electronic brain. Like it is like a single neuron, but when I say single neuron, it was an electronic circuit, okay, but it was not able to learn. And then in the 57, you had this perceptron. Again, it was a single neuron, but it was able to learn. It could learn something. And the part that you see here, 1960 to 70, this is called like the golden age of AI, right? Means many people, many researchers were interested in AI. There was a lot of funding available and so on, right? But unfortunately, this part, right, like 70s to late 80s, this is called AI winter, right? Means this is the dark age of AI, nothing much happening, not much research, not much funding available. And all this changed in the late 80s when the backpropagation algorithm was actually proposed, right? Because it allowed training multi-layered perceptron. Previously, you only had a single layer in the network because there were no algorithms to train a multi-layer perceptron. They were, but they were very trivial, right? So backpropagation, you must know from your knowledge of machine learning, is an algorithm that you use with neural networks, right? And it was proposed in 1980s, late 80s. So it means in this area, NNs were very popular, but in the late 90s and early 2000s, SVMs were introduced. So you see, again, you can say this was like near to death of ANN because no one was using ANN in early 2000. Every paper, if you see paper in the area in the region of like late 90s and 2002, 3, 4, every single paper would be using SVM as a classifier. Okay, no one, hardly anyone, you will find that people using ANN. But again, in 2010, okay, basically people again shifted back to neural network, but this time with deep neural networks, right? So we'll come back to this because this is where we have to start our discussion. Okay, so what is it that contributed to the current fame of deep learning, right? So there were two contributing factors, right? One is, of course, data, that you have data available. People started labeling data, making it available to the community. And then you also have the computation power, right? Maybe the algorithms which you were not able to run on CPUs, thanks to the availability of GPUs, now you could run them very, very fast, right? And NVIDIA has played a very good role in promoting, you can say, deep learning research, especially on the GPU side. Many of you must be knowing that about a few years back, if you are a researcher or faculty member, you could request NVIDIA for a free GPU, right? They would send you a free GPU, you could do research and you could run your algorithms. So this continued for like 2 years, but later on they closed the program. Okay, so how deep learning has affected different areas, right? So you see, it was applied to speech recognition in 2009, then computer vision 2012, and then machine translation and in 2014. And since then, almost everything that you see today, you will find the solution implemented with deep learning. So another impact of deep learning is that previously, you see, people have been working in NLP, right? People have been working in computer vision, machine learning. So they did not have anything common, right? Means they did not have any common terminologies. But today, by today I means since deep learning has come to scene, this has changed completely. It means if today I'm solving a computer vision problem, I will be using machine learning or deep learning. Similarly, if today I'm solving an NLP problem, so I'll be collaborating with someone from machine learning or deep learning, and I'll be using those techniques to solve my vision or NLP problems. Okay, so some people would say that whether deep learning, the hype that it has created, whether it is worth it or not. So just it's a debate, but if we see the people who actually have been the founders, or you can say the fathers of this domain, so they actually believe that what you can do with deep learning, there is actually no theoretical limit, right? So many algorithms, for example, once people were solving them with conventional techniques, so as soon as they applied deep learning techniques, so the gain was very, very significant, right? And what you see here, knock over benchmarks, what does it mean? That maybe suppose I'm solving a problem like, say, face recognition, right? So we are trying very hard something. So maybe I'm just telling you, okay, these are just to give you an idea. Maybe with all efforts, we reach like 85%, 86%. But as soon as we transform to DL, so maybe it jumped to something like this, okay? These are just hypothetical numbers, not the true numbers, okay? I'm just giving an idea. So you see the jump that people achieved in different problem domains, that was very, very significant. And just to further, you can say, advocate this point, you can go to Google and you can search, you can go to trends.google.com and you can give a keyword and see how people have searched it, okay? So you see here initially it's a flat curve, nothing at all, right? But all of a sudden you see this rise, that more and more people are becoming interested in deep learning, right? So this again advocates that all the hype that is there, to some extent it is actually justified. Okay, so maybe I'll take a small pause and I'll let you talk. So if anyone wants to say anything, you're welcome. Okay, so you see, why is it so that with deep learning, all of a sudden you have so much of performance enhancement, right? So if you see this curve, right? So if you are talking about traditional machine learning algorithms, right? So we know that if we provide more training data, okay, then we know that the performance increases. But after a certain point, the performance becomes stable. Okay, means even if you keep on increasing the data, you won't see a significant increase and the curve would be almost flat. But with deep learning, it's not the same thing. What happens that as you increase the amount of data, the deep learning based solution are theoretically they would be enhancing your performance. Of course, this curve would flatten, but at a very later stage. You see, maybe when you arrive here, you already have gained a lot in the performance as compared to a conventional method. So it means, in simple words, if we summarize this slide, more data, better the performance, right? So this is the one key difference that you can state between conventional machine learning and deep learning. Okay, so now if we formally define deep learning, if you write in Google definition of deep learning or something like that, right? So maybe it is something like that, that it is a subset of machine learning in which we are interested in algorithms which are inspired by the structure and function of the brain. In other words, we are trying to say that deep learning is a branch of machine learning where we want to design algorithms which are very similar to the way a human brain works, right? So you see, this definition does not seem very appealing. You would say, okay, machine learning was or neural networks are the same thing, right? So what is new here? So let's slightly change this definition to a layman definition, okay? And the layman definition is that deep learning is just a brand name, nothing else, right? It's just a brand name. Deep learning is the study of neural networks. Okay, so when we say deep learning, we are not talking about anything. We are just talking about neural networks. But the only difference is that the neural network will have many layers between input and output. So what you see here, it's a simple one-layer neural network. This is your input layer, and this is your output layer, and maybe you have one or two hidden layers in between, right? So when we are talking about a deep neural network, which simply means that you will have relatively larger number of layers between input and output. Okay, now this is debatable that what you mean by deep. What is deep? Whether 5 is deep or 7 is deep or 100 is deep or 1000 is deep. Okay, so this is a relative term. So maybe if you talk of the early days of deep learning, so like 8 layers or 15 layers, it is very, very deep. But today you have networks which have like 200 or 100 layers. So if you compare them, then you will say 16 is not very deep, right? So it's a relative term. But still, when you compare them to the conventional neural networks which existed before deep learning, you will not find more than 3 or maximum 4 layers, right? This was the maximum. You won't find them, right? Because with those conventional methods, if you add more layers, you risk suffering from overfitting, and then you will need more computational resources to train, which were not available at that time, right? So in simple words, if someone asks you what is deep learning, okay, you are doing masters in data science, you appear in a job interview, someone says what is deep learning, so the simplest way you can tell them is deep learning is simply the study of neural networks in which we have many layers between input and output, right? It's just a brand name, nothing else, right? And you already know neural networks, so I hope this course won't be much difficult for you. Okay, there's one more difference that we can identify between conventional machine learning and deep learning. And what is that? Okay, please see this one carefully because this is important. Let's suppose you want to make a classification system which can tell you what is this object, okay? So if you are talking about conventional machine learning, what you will do is you will think, okay, what are the features I need to extract? For example, if you have to identify cars, then you will say, okay, maybe I can find these ratios, or what should I do? What is the ratio of this part to this part, or anything that you can think of. And then whatever features you have extracted as an expert, you will feed them to a classifier. And then that classifier will tell you whether the object you are talking about is a car or it's not a car, right? But when we talk of deep learning, the key difference is that this part, right, is which was previously being done by a person, by a human, right? Means a human was thinking, what are the features I should extract? Now this part of feature extraction and classification, both of these parts are in one single block. You see here, this is your neural network. So some part of this neural network is extracting features, and some part of this neural network is doing classification, right? So this is one of the key differences, that when you talk of conventional machine learning, you have a human expert, domain expert, who is designing features. So that's why we use the term handcrafted feature. And when you are using deep learning, you don't need any domain expertise. You can simply input the data, and the network can automatically learn what are the features that should be used for this particular problem. Okay, so
okay, let's resume our discussion. So we have seen some preliminary things, what deep learning is, how deep learning fits in your overall degree program, right? So now we are in a position to see what the course contents are, right? So for the first couple of weeks, we'll be talking about neural networks. So you must have seen these in your previous course, right? But today we'll revisit them. So this will take around two weeks. The first point, which is like ANN, backpropagation, what are activation functions, and so on. Then we'll be starting our first topic, which is the main topic from deep learning, which is like CNN. And then we'll see some CNN architecture. So this will take around easily 3 or 4 weeks, right? These 2 bullets. And then just before the midterm, we hope to complete this autoencoder, right? So this part till here, we expect to finish it around midterm. And then After midterm, we'll start with sequence modeling or RNN, right, in which we'll see LSTMs and different variants. Then we'll see how you can use deep learning for object detection. And of course, if we get some time, we'll dedicate 1 week to generative adversarial networks or GANs, right? And throughout the course, we'll be having different case studies, okay? And of course, as I told you earlier, that I'll be introducing you to some deep learning libraries that will be helpful for you in doing the assignments, okay? So most of the examples that we'll do in this part, okay, which is related to CNN, okay, so they will be mostly based on image data, right? And when we are dealing with this part, we'll be mostly dealing with text data, right? So this part you can correlate with computer vision, and this part you can correlate with NLP, right? But it does not mean that you need to have those expertise, right? They are totally different courses, but CNNs are primarily meant for image data. So the examples that we'll do, they will have almost in all cases images. Similarly, in case of recurrent neural networks, we'll be mostly doing examples which will be based on textual data. Okay, so now let's talk about what deep learning software or what languages, what platform, what libraries we expect you to learn in this course, right? So you see, as you must have already guessed that we'll be doing Python, but I would like to justify why we are doing Python, right? So this is some data, not very old, last year collected by job advertisement, right? Means the jobs that are related to data science, right? So you see 90% of the jobs which you find in data science, they require Python as a keyword, right? And then you have R and SQL and so on, right? So you see, this will not add up to 100% because one job ad can have multiple terms, right? So if you are wondering why the sum is not 100%, it is because if there is a job ad, you can have multiple requirement of multiple skills. But irrespective of that, so you see easily at the top, whenever we talk of data science, we talk of Python, right? That's why even if you have not done Python before, I'm not expecting you to be an expert programmer, but with some basic tutorials, you would be able to write programs, right? So, and as I told you that once you have those basic building blocks available, you can always borrow implementations from the internet and you can come up with your solution. That is perfectly fine, okay? Okay, so will be, of course, the initial implementation that you will be doing, simple machine learning, which is a simple neural network, right? For which you will be needing certain libraries like scikit-learn, NumPy, and pandas, and so on, right? But when you talk of pure deep learning, then there are many options available like TensorFlow, Keras, Theano, PyTorch, and so on, right? So I'll tell you which of these we'll be using and again why we are using it. So there are many interesting analyses which are available on the internet, which actually compare which is the most popular deep learning library, right? And this is one graph that I could find. You can see the source at the bottom of the slide. So this data has been collected based on you can say job postings, GitHub source codes, and archive articles, right? And easily you see TensorFlow is the most, you can say, widely used deep learning library, right? Which is with the absolute score is like 96%. Okay, and interesting thing is that I think this data is about 2 years old, or at least 1.5 year old. At number 2, you have Keras, right? But this was true maybe 2 years ago. As of today, TensorFlow has acquired Keras, right? Now, Keras and TensorFlow, they are not two separate things. You just install TensorFlow and you have Keras. Previously, it was the other way around. You first used to install TensorFlow, and Keras was actually a wrapper for TensorFlow. But as of today, this is not true. So it means now both of these, actually, this is one single bar. So you see TensorFlow today, if you are talking about deep learning in Python, you can blindly use TensorFlow. Of course, in special cases, you may have certain specific requirements of your client, but if there is no such constraint, you don't need to think over it, right? You just go for TensorFlow. Okay, now I'll come back to TensorFlow. I'll tell you how to install it, how to install Python and everything, right? But before that, I'll take some time to discuss some common deep learning data sets, okay? And why we are talking about this, why do we have certain benchmark data set? The reason is that You see, whenever you develop a new algorithm, you have to, you want to see how good your algorithm is, right? So there are certain benchmark data sets that, first of all, you will test your algorithm on those data sets, right? Because everyone is testing their own algorithms on the same data set. So there will be a benchmark. You will be able to see how good your system is, right? And then you can, of course, use it to any other problem. So like any other community, we have some very classical data sets available, you can say, in the deep learning community. And whenever we make some new contribution, it's always a good idea to first test how our contribution works on benchmark data sets and then actually go on and apply it to a specific problem. So the most classical data set, which is available even before deep learning, people have been using it for conventional machine learning, is the MNIST data set, right? It is a collection of 60,000, you can say, training images. These are classes 0 to 9 and handwritten digits. Okay, so it means someone has written these numbers, and there are, of course, multiple contributors. These are not by one writer, there are many writers. So there are total 70,000 images, out of which 60,000 are like training set and 10,000 are test set, right? And there is an equal distribution of each image. This is one of the most, you can say, classical data sets. So it is so classical that when you install TensorFlow, you just write a command down, load data, and the data set is automatically downloaded. Okay, you don't need to manually download it. You can write call a function and the data set will be automatically downloaded in your machine in a temporary folder, right? So your few of your initial assignments would also be based on this data set, right? So this is a data set that you will be using frequently, at least in the first 3 to 4 weeks of the semester. Then again, a very popular data set for deep learning, which you will see people using very frequently in their experiments, is the C410 data set, right? 10 is actually because there are 10 classes. The previous data set, these were like grayscale images, I mean, there's no color information, right? But here you have 60,000 images in 10 different classes, like a car, aeroplane, something like that. But the difference is that these are not colored images. Like colored images are like RGB images, 3-channel images. So there's more information in a colored image as compared to a gray image, right? So otherwise it has almost same number of classes and almost same size. MNIST was 70,000, this is 60,000, right? But the key difference is the color information. Okay, then this is a data set that you will frequently see reported in many papers, many presentations, ImageNet data set. Right? It is actually a very huge data set, more than 14 million images, but all of those are not labeled, right? There's a small part which is labeled, and that part is still, I think, more than 1 million. So they have 1,000 object categories, right? And this is the same data set which in the first half of the session, I told you that there was a major milestone in which computers were able to see better than humans. So those experiments were actually performed on this data set, right? And previously there used to be an, you can say, international competition, which is called Large Scale Visual Recognition Challenge, in which different teams all over the world would submit their algorithms, and then there's a ranking that which algorithm is the best in recognizing object, right? And it is the same data set which actually led to the current popularity of deep learning, right? So I'll come back to this data set later on when we are studying convolutional networks, right? But this is a data set that the discussion of deep learning is incomplete if we don't mention this particular data set, right? Then a little later we have MS COCO. It is like again a very big data set, more than 330,000 images with 80 object categories, right? And it is used not only for classification tasks, but also for other tasks like object detection and image capturing, right? So again, we'll come back to this data set when we are studying recurrent neural networks, right? I'm just telling you names and showing you some pictures so that you get familiar with them. The technical details of these data set we'll be discussing when we are actually using them to solve a problem. Okay, this is again an interesting data set which is called Fashion MNIST, right? So you see, it is inspired from MNIST, same 70,000 images in 10 classes, but instead of digits from 0 to 9, now you have shoes and bags and shirts and so on, right? So these are 10 different categories, so they called it Fashion MNIST, right? So this is again a good data set if you want to test your algorithm. So all of the previous data sets, they were actually based on images, either color or gray images, right? So we also see a couple of data sets which are based on textual data. So a popular data set is basically IMDB Reviews, where you have around 50,000 records. These are basically the comments or the reviews of different movies, and every review is categorized either as a positive review or a negative review, right? So it actually can be used for sentiment classification problem, and more specifically binary sentiment classification, that whether the person liked the movie or did not like the movie, right? So again, when we are using RNN, we'll be using this data set. And finally, we have this data set, again, a textual data, where we have 20,000 small short paragraphs, which are taken from different groups of news categories, right? What does that mean? That, for example, whether this text is related to weather or sports or politics or religion and so on. So there are 20 different categories of news, and we have a small text, and the idea is to categorize that from which class this particular text belongs, right? So this is again a data set that you can use to test your algorithms which are solving some NLP problem. So other than that, there are many data sets available, like for sentiment classification, machine translation, song data set, and so on. So if you are interested in data sets, a very good resource is Kaggle. You can always go to Kaggle and see what are the new competitions and what are the new data sets that people are making available. And there's one more thing I would like to say, that if you are interested in solving some local problem with local data, so there's a very good resource, opendata.com.pk, right? You can go, you will find a lot of data related to crime, related to different surveys and so on, right? And all that data is collected locally. Means that is, if you are trying to address a local problem, then of course you need local data, right? You cannot generalize data on data which is collected from other countries, right? So it's a very good resource. You can explore it, and maybe if you are planning to do a thesis, so you can find a good data here, and you can base your research on that data with the idea of solving a local problem. Okay, so after these data sets, just a few comments that why do we need deep neural networks, right? What is it that is forcing us to use deep neural networks, right? So you see, what is the objective? That we need to recognize something. We need to recognize a pattern. If I show you a picture, by you I mean the machine, then we expect the machine to tell what is it, right? Which is the traditional classification framework. Okay, so previously, you know that with computers, we can do very heavy repeated calculations, but they have not been very good in recognizing patterns, right? Maybe if you ask a computer to do some calculation, it will do it. But if you show it a picture and ask it to tell what the object is, then you need a very sophisticated algorithm to actually make the computer recognize what is it looking at. But with deep learning, this has changed, or you can say is in the process of being changed, right? Means that computers are becoming more and more, you can say, better, or they are improving in terms of recognizing patterns. So you see, if you're talking about how much is the complexity of my problem. So if your problem is simple, right? For example, if you are trying to recognize digits, then maybe a simple method like SVM, that is sufficient, right? It will give you good results. But as the complexity of your pattern increases, right? So the neural networks or the deep neural networks, they start to outperform conventional methods like SVM or other classifiers, right? And if the patterns are very complex, then deep networks are actually the only choice, because if you apply conventional techniques, they will not work very well on, you can say, such complex patterns which you are trying to recognize. Now, what is the key idea of deep networks? It's a fairly simple idea that is again inspired from the human brain. And the idea is that whenever you have a complex pattern, you break it into simple patterns. This is a very simple idea on which the whole of the deep learning relies. Now, what does that mean? If I show you visually, let's suppose you want to recognize faces, right? So what are the small patterns within the face if we are trying to recognize a person from a picture? So the components of a face are like parts of the face. Okay? So we can break it into small parts like eyes, nose, lips, ears, and so on. And then we can further break these components into still simple shapes like straight lines, curves, or edges, right? So this is the whole idea. And throughout the course, this whole idea will be revisited again and again, right? I'm just telling you from an abstract layer that this is the general idea, but you will be convinced that actually it is happening once you study convolutional networks and other related topics, right? So this particular concept will keep repeating again and again, that what we aim to do is whenever we have a pattern, we try to break it into simple patterns. And the good thing is that this is actually how human brain works, right? So you see, whenever you see something, so this is your eye, right? And this is your retina. And this retina is connected to the back of your brain, right? Whenever you see something, the back of your brain, which is called visual cortex, right? This is called visual cortex. This is responsible for whatever you see. So you see this division of visual cortex. So this what they call V1. So it is actually helping you to recognize simple shapes like edges and lines, right? And whatever it has recognized, it is feeding to the next set of neurons, which we are calling V2, which is actually combining these and making some meaningful shapes, right? And as you progress, these shapes start becoming more and more complex and abstract, and eventually you are able to recognize that this was actually a face. So you see, if you correlated the same thing with the network, right? This is a neural network or a convolutional network, right? So what is actually happening is that you see something that you have different parts of the brain which are actually performing a hierarchical recognition of what is going on. So same thing actually happens within a network. You have some part of the network. If I feed it with the image of a cat, so maybe this part of the network is learning or telling like curves or straight lines or edges or something like this. Then these subsequent or intermediate layers, they combine them, okay, into some meaningful shapes, and eventually by the time you arrive at the last layer, the network is able to tell you that the object it has seen is cat. Okay, so there are very high similarities, or you can say, between how a DNN works and how human perceive the objects. And these similarities will become more clear when we actually see how these CNNs are working. Okay, so when you have a problem to solve, okay, you will have many choices that, okay, although you have not seen them, but I have shown you the course contents, right? So of course, we'll see them from in the subsequent weeks of the semester. But in some cases, if you are solving a problem, it's a good idea to generalize that for what type of problem, what should be the solution, right? And later on, we can have the technical details of that solution. Okay, so if you have unlabeled data, okay, and I assume that you know from machine learning what is unlabeled data, something like this. For example, when you are doing clustering, you have unlabeled data. There are no labels, right? So if you have unlabeled data, then you can use restricted Boltzmann machine or autoencoder. So autoencoder is something that we'll cover when we are dealing with unlabeled data, or you can call it when we are dealing with unsupervised learning. When you have image data, right? You have labeled data and you want to recognize, say this is your machine, you want to tell what is this object, then we'll be using convolutional neural networks, okay? Again, we'll study it in, I think, third week of the semester. As I told you earlier, if you have text data, you are solving an NLP problem, then most likely you will be using a recurrent neural network, which is called an RNN. Okay, so this will be looking at after the midterm. And if you have a problem like speech recognition, that if someone is saying something and you want to generate the textual transcription, then again, it's a sequential data, so you will be using a recurrent neural network, right? So this is a general, you can say, categorization that for what type of problem, what could be the solution, but it does not mean that this is the only solution. It is always possible to combine a recurrent network with a convolutional network and so on, right? But these are the general guidelines that if you want to make a hello world of speech recognition or a hello world of like text processing, then your first choice should be a recurrent net, right? Of course, you can always improve on that and combine different solutions to come up with an enhanced solution. Okay, so maybe I'll tell you this later, right? But now I would like to hear from you, because if it's only me who is talking, then I have video recordings available. I can just play the video. The whole idea of live session is that we can have some discussion, right? So I'll be taking a pause, and I would like to have some comments or at least some questions from you, because if you don't ask any question from next week, I have recorded video, I'll just play it, right? And maybe you can find better videos on the YouTube, right? So when we are having a live session, we expect at least some sort of discussion, okay? So I'm just pausing it for the time being, and I would appreciate if you have some comments or some points or some queries.